And our next talk is model-based engineering with AADL, transitioning research to practice by Sam Proctor. Sam is a senior architecture researcher and initiative lead of the model-based engineering team here at Carnegie Mellon University's Software Engineering Institute. There, he studies architecture-centric model-based engineering problems, particularly those related to safety and assurance. Here is Sam.
Hi, my name is Sam Proctor. I am the initiative lead for the model-based engineering group here at the Software Engineering Institute. Today, I'm going to be talking about how the Architecture Analysis and Design Language, or AADL, helps us transition research ideas into practice. So this is a roadmap of where we're going today. We're going to be talking about the problem space that I work in, how AADL helps my teammates and I solve those problems. The DoD's recognized that, and we have seen some success in DoD projects. And then we'll wrap up by talking about how AADL aligns with DoD's digital engineering strategy. So let's talk about safety critical embedded software systems, which is sort of a mouthful, but these are basically cyber physical systems that if they fail, are going to cause some sort of unacceptable loss. So think medical devices, aviation, certain automotive components, things that might cause a mission failure or an unacceptable amount of money to be lost, or even injury or death to a human if they go wrong. These systems are built in such a way that often issues are created sort of early on and caught later on. So issues are created in the requirements phase or when components are being designed, but then those issues aren't discovered until until the components are actually integrated together or the requirements are being tested. So the idea is to discover system level issues early by annotating components and then virtually integrating those components. Our solution has two prongs to it. We have a language, AADL, which is internationally standardized. So it's not something that we've just come up with in a research project and are going to abandon. It has over 15 years of use in academia and in industry. Then at the SEI, we also developed tooling to support that language. We created an integrated development environment called OSATE, or the Open Source Architecture Tool Environment, OSATE. And OSATE helps system designers write AADL, and then once you have an AADL model, helps them analyze it for various system level things. So you can attach component level latencies to your individual components and come up with an end-to-end latency once you have the system specified. So I'm generally uncomfortable talking about AADL without giving at least a flavor of it. So first we're going to give a short overview of AADL itself. AADL has two syntaxes, a graphical and a textual one. And the graphical syntax is what we're going to be using in these slides, though if you're a computer scientist like me, you might find the textual one, which is declarative in nature, a little bit more comfortable. Its graphical syntax, though, presents boxes and lines, just like engineers are drawing on whiteboards all around the world. The difference between the boxes that AADL lets you draw and those that are drawn on a whiteboard is that the semantics are precisely specified for AADL. Using mathematical descriptions, we know exactly what they mean. So, for example, this box on the slide now is a temperature control process that might be used in something like a smart building to keep a room at a comfortable temperature using a computer to govern whether or not we need to turn on a fan. As a process, it is a protected region of memory, and we can allocate threads there. Now, it's likely that if you were just drawing this on a whiteboard, you could say all of that if you were well versed in system design issues. But what's the likelihood that someone looking at the whiteboard later on would come up with the exact same definition of a process that you would? Maybe not as high as we would hope. So that's the importance of standardizing the precise specifications of meaning that AADL enables. So we can put some threads in our process, something for a temperature sensor, a thermometer, something for a controller, a little bit of computational logic to say if the temperature is out of bounds or not, we should turn on a fan or not. And I promised you some lines, so now we can draw lines between those boxes. We can connect these threads, in this case, together with different types of intra-process communication, but we need to differentiate some of the behavior of our threads. This is where we can use AADL's extensible property mechanism, which lets us specify additional semantics to attach to various components and connections. AADL comes with a number of properties, but if you find that there aren't enough, it's easy to come up with your own properties and then use those to guide additional system analyses or code generation. In this case, we'll talk about the dispatch semantics and how those would be added with a property. Our temperature sensor is a thread that should wake up periodically and check if our room in our smart building is at a comfortable temperature. It will forward that temperature to the controller, which can decide whether or not, according to some configuration, that temperature is acceptable or not. If it is acceptable, then we don't need to do anything, but if it's not acceptable, we can turn on the fan. So what's key here is the temperature sensor needs to have what we call periodic dispatch semantics. That is, that the sensor should check according to some clock. Every once in a while, without any external interaction, it should just check the temperature. The fan, however, should only be turned on or off when the controller says it should be turned on or off, that is, using sporadic dispatch semantics. If we were to use periodic semantics for the fan, we would have a problem because the fan would turn on and off at the same rate, whether it was a hot day or a cold day, and our room probably wouldn't be very comfortable. So it's this sort of notion that we need to embed, and we can do that using AADL and the property specification mechanism. So that is the world's quickest overview of AADL, but I hope that it gives sort of a flavor for the language, because now we're going to shift gears a little bit and talk about how AADL helps us solve problems, how we use those formal specifications of developer intent to learn system level things, having annotated only the components in a system. So I'm one of the PIs on the Integrated Safety and Security Engineering project, also called ICE, and like the overall approach that we take in the model-based engineering initiative, we have a two-pronged solution here with tooling and language extensions. These are some of the high-level tasks that we did as part of the ICE project. You can see that there are several of them, mostly tooling extensions, but also some modifications to AADL itself, like a new annex to the core language that lets system designers annotate their security requirements and how their system is going to go ahead and meet those requirements. But we can also talk about the various tooling aspects. Some of these are pretty stable, like descriptions of the library of error models that we have. The error model v2 library there on the left is maybe one of the more stable tooling artifacts that was produced as part of the ICE project. On the other end is the architecture supported audit processor, which is, or ASAP, which is very much a prototype, but we think is a really exciting concept for the future of hazard analysis. So these different tasks, unfortunately, I don't have time to go into in great detail, but just to give a flavor of the type of work being done in this project, we can talk about the safety patterns. So the safety patterns task was headed up by a colleague of mine named Jerome Hugh, and the idea here is that there are a number of safety patterns that have been published in the literature, things that you should do if you want certain safety characteristics in your system architecture. So for example, if you want some part of your system to be immune to a single point of failure, you might use what's called the triple modular redundancy pattern, where you have 3 sensors and they vote. So if one of the sensors fails, the other 2 can outvote it and you'll still have correct sensor data. Unfortunately, achieving triple modular redundancy is not as straightforward as just getting 3 sensors and hooking them all together. You have to be pretty careful about how everything is configured, or you can still be vulnerable to a single point of failure. So what Jerome did was, using previous research projects, or the output of a previous research project called Architecture-Led System Assurance, he actually specified how triple modular redundancy architecture should look in AADL. And then those AADL models were embedded using an example mechanism into OSATE, the open source architecture tool environment, or SEI tooling for AADL. So now if you download OSATE, you can get the safety patterns shipped with it. That's available right now. Other research projects previously studied how to model errors in your system. That's the EMV2, and this was not done as part of ICE, but rather we built on it in this project. That's actually sort of a theme that I want to highlight, is that there has been a history of architecturally integrated safety and security work that has been done here at the SEI and then embedded into AADL and OSATE. So as you can see, in 2006, which is shortly after the original version of AADL was published, we noticed that users wanted to extend the notion of their component interface to include what we call off-nominal or rainy day behaviors. The idea here is that if I've described my sensor using AADL, I should be able to describe the various ways that it might fail. That way, when I compose my system, I can think about how that sensor failure might impact the overall system's ability to do its job. This research is actually already transitioning to practice. As you can see, we revised the error model and totally overhauled it in 2014. And now multiple contractors in the Joint Multi-Role Mission System Architecture Demonstration Program, or JMR-MSAD, are using AADL in addition to the EMV2 Annex to describe various system components. And they're able to do this because this work was described in an annex to the core AADL language and supported via our open source tooling, OSATE. So they don't have to go out and read my paper, they don't have to go out and read Jerome's paper or the publication of any of our colleagues. They can get this knowledge just by downloading our tooling. As you can see, the safety work continues, and in the future we're going to be looking at increasingly autonomous systems and how we might model the various ways that things might go wrong so that we can think about how to make those systems safer too. Safety is only one line of research, though, that has been conducted using AADL. This is a more holistic view of the lines of research enabled by AADL. And it's not that AADL is key to, say, code generation research or behavior, but rather that AADL works with code generation technology. So if someone publishes a cool idea on code generation or requirement specification, or maybe resource budgeting and latency, that idea then can be embedded in AADL. The algorithms that are developed can be encoded in OSATE. And so then downloading this tool, OSATE, using AADL as a language, lets you get access to this research. And so we've seen a number of projects in DoD projects, are shown here in blue, non-DoD projects in green, use various research ideas by using AADL and OSATE. So we've had users, of course, within the DoD that we're going to talk about more, but also groups like the European Space Agency, the Food and Drug Administration here in the US, a number of organizations that work with safety critical systems have found value in AADL's encoding of various research ideas. So let's talk a little bit more about that DoD impact. Specifically, I want to be sure and highlight the story of Army Aviation, because we have really had this tremendous partnership with the U.S. Army. If you were at the research review here at the SEI in 2019, you would have seen a presentation that I gave jointly with Alex Boydston, who works with the U.S. Army, and he talked about the benefits of AADL and ACVIP, or the architecture-centric virtual integration process, which really is the process by which we say this is a good way or the correct way to use AADL to specify components and virtually integrate them. It's that architecture-centric virtual integration that I mentioned early on in this presentation. So Alex and the Army have found that there are a number of benefits to AADL and the ACVIP process that let you find problems early, let you reduce risk, and also, like we studied in the IC project, increase cybersecurity, because there are fewer gaps in the understanding of a system than you might have if you write your requirements out using narrative English. So this is particularly important in things like aviation, or in domains like aviation, because certification plays such a huge role in getting these systems built and getting them fielded. And so certification authorities, of course, appreciate unambiguous statements. So these unambiguous statements in languages like AADL can support certification for airworthiness, safety, cybersecurity, and things like that. It's not just the Army that has found these benefits, though. One of the key research projects that we built on in ICE was DARPA's Hackams project, or the High Assurance Cyber Military Systems. The idea here was that academic and industrial performers were asked to create an attack-resistant system. And DARPA Labs was contracted as a red team to test just how attack-resistant these systems were. Collins' team used AADL and the research outputs of previous SEI research projects like that architecture-led system assurance and created a system that DARPA was unsuccessful at attacking. This is notable because every other system in the competition was successfully compromised. So AADL was not the only technology used, but it was sort of the architectural backbone that defined the components, gave them strict component definitions, these unambiguous statements of what was and was not intended to be in the system. And so there were fewer gaps then for the red team to exploit using their various techniques. AADL's use by both researchers and practitioners enables a really smooth transition pathway from research to practice. So you've likely heard of what's called the Valley of Death, which is the gap between academic research and industrial use. The idea that there are researchers like the Software Engineering Institute or Kansas State University, maybe Telecom Paris or Invenium Labs, that have cool ideas, and they describe these ideas using maybe mathematical statements or custom languages that a grad student whipped up and used for a couple of years. And then there are industrial users that have very concrete needs. They need problems solved. They're facing budget overruns in terms of time and in terms of cost. And so these users like the Army and Dassault have these concrete needs. But they're separated because a lot of times the research outputs are not directly usable by industry. So this is what we mean by the Valley of Death. AADL helps us bridge this valley because the researchers, in this case SEI, K-State, are using the same technology that the industrial practitioners are. So when I come up with something cool, when Jerome comes up with something cool, or a colleague here comes up with a neat idea, they can encode that in AADL, and that can be standardized and then used by practitioners. If a colleague at GTRI or at Invenium Labs comes up with a neat algorithm for model-based engineering, that can be encoded in OSATE and downloaded by the DoD and industry. We don't have to rely on someone finding our paper, understanding all the math in it, and building their own implementation. Instead, they can just use our tools the way they have been using them and get access to the knowledge that we have embedded in there. So that's really AADL's tool as sort of this bridge from research to industry that makes it such a pivotal technology and a fun one as a researcher who likes seeing his work used to work with. So now we're going to look forward a little bit and talk about the digital engineering strategy. So as you may be aware, in June of 2018, the DoD published its digital engineering strategy, and Michael Griffin wrote that the document described what the goal was, but those implementing the practices had to develop the how, or the implementation steps necessary to apply digital engineering in each enterprise. What has happened in a lot of cases is that there are a series of digital models that provide an authoritative source of truth. So think CAD or computer-aided drafting models for design. They are authoritative and can be used in a formal development process. We think that AADL can be used for the safety critical embedded systems as it is a model that supports integration, that virtual integration that I talked about earlier. It supports these formal development processes, and notably, like the second tenet in the graphic here on the right, it provides this authoritative source of truth. You can embed the knowledge that you have about your system at a given time using AADL properties, and those are unambiguous, and they can be shared with other system designers, with certification authorities, and the various types of entities that need to know various types of details about your system. We at the SEI are not the only ones that have had this recognition. Alex Boydston, that gentleman from the Army that I mentioned earlier, as well as Peter Filer, a scientist here at the SEI, and two scientists from Advenium Labs, published a document that said that the architecture-centric virtual integration process plays this key role in addressing problems with cyber-physical systems and can be this key contributor to the digital engineering strategy. So the takeaway that I hope to convey is that AADL is a tool that you can use whether you're on the more research or the more applied end of the system development spectrum. So if you want help, or if you have questions, or if you just want to learn more, please reach out. Thanks.
Thank you very much, Sam. That was a fascinating presentation. We really appreciate it. A couple of questions we'd like to throw out to you. You talked a great deal about transition and effectiveness. Can you also maybe share with us your thoughts that you have on AADL's role in safety and in security?
Absolutely. So safety and security are both, near to my heart. They're close to my research area. And one of the reasons that I really like working with AADL is that it has an extension to the language that I think I mentioned briefly in the presentation, specifically for modeling errors or off-nominal behavior, or basically things that can go wrong in your system. That error modeling annex is now in its second revision, so it's called EMV2, and it is really great at documenting both safety and security problems. In a recent research project, we developed a security-focused annex to the language that is close to publication, as well as some prototype tooling for verifying security properties about your system. But I also just want to emphasize that just having an unambiguous statement of designer intent, like you get with AADL, can really eliminate a lot of the problems that malicious actors are able to exploit to cause security problems. So in many cases, we see that there are just fewer security issues with a well-engineered system like you'd get with AADL.
Great, thank you. There's another question here that came in from the audience, which I think is quite interesting. Can you address how the findings of the ongoing development projects such as ISSE are influencing AADL version 3?
Absolutely. So the project being referred to there is IC, or the Integrated Safety and Security Engineering Project, really drove home the need for a unified description of system behavior. Right now, there are a number of ways to specify behavioral aspects of a system in AADL, some like the error modeling annex for off-nominal behavior, other for nominal behavior, and some for mode changes between a system. We did some early work under IC at unifying these behavioral specifications, and that work is continuing under some newer projects that are starting up here at the SEI. So this unified behavioral specification is going to be one of the big drivers behind AADL v3. So that's a good example. There are some other smaller ones, but that's one of the main findings coming out of IC that will impact AADL v3.
Okay, thank you. You also mentioned many of the capabilities you described. Some are available now and some are starting to transition into practice already. What do you see as the overall time frame for moving most of these capabilities to engineers and practitioners?
That's a great question, because one of the things that makes AADL and its related tooling very powerful is that there are always tools that are sort of in a more prototype stage and tools that are maturing and ready to be used by practitioners. So to some extent, the way it works is that we come up with more academic-driven ideas and tools, and then float those out to practitioners who say, we like these ideas, but they really need to be customized to a DoD context in this way, or we like what you have here, but it's maybe not ready for the prime time, or sometimes it is. But what we do is we develop earlier work and then work closely with our DoD and industrial partners to tailor it to their needs and make sure it's ready to go. So to sort of answer that question, in one concrete way is hard because there will always be a prototype that's being transitioned, and there will always be mature tooling that's ready to go and meet some of the needs of our practitioners now. Does that answer the question?
I think so. We had a follow-up question, which goes into this, which is one person asked, how can I get started as a software architect integrating AADL in my daily work?
That's a great question. So I think the first thing that you can do is go to osate.org. That's osate.org, which has instructions on downloading and installing the open source AADL tool environment, or OSATE. This is the AADL tooling that we develop and maintain here at the SEI. So that will give you a tool environment that will let you play with AADL, and it comes with examples that you can load right into the environment and start checking it out, playing with things, seeing what works, how to specify things, and then verify various properties of your example system. So I would dive into OSATE, and if you have any questions, email us at info@sei.cmu.edu, and we'll be happy to help.
Great, thank you. Just a couple of notes here for people. We're going to move into a roughly 20-minute break now. We will return at 10 minutes after 1 p.m. Eastern Standard Time. And also want to assure everyone that the talks, the slides, the videos will all be available in the SEI's online library, and that we will send a link to everyone when those artifacts are ready to be viewed. Thank you very much. We'll see you at 10 minutes after the hour.